Okay, so here's what we were talking about last time. We were talking about level sets. Now, this is a certain point of view that you can take on level sets. This is a picture demonstrating the way in which level sets relate to graphs by way of cross-section. So specifically, if you have a graph, right? So this is what a graph of a function in two variables looks like, the surface in R3. If you have a graph, the act of taking a level set of it, slipped over my own language. The act of taking a cross-section, a horizontal cross-section of it, you might even say a level cross-section of that graph. Notice that gives you two equations, the combination of which amount to setting f equal to a constant. Right? So that intersection is is a level set in the sense that f is equal to a constant on that collection of points. Now, the asterisk awkwardness, of course, this collection of points is a collection of points with x and y coordinates that obey the equations in question, but they also have a z coordinate. Technically, this cross section is a curve sitting up in 3 space, right? Technically, the level set is what you get when you throw away those z coordinates. The level set is a curve in the domain. It's a curve in 2 space. But anyway, it's kind of a formal asterisk. But modulo that asterisk, cross sections of graphs are level sets. Okay, so we talked about that last time. We did a couple of examples, and then I made the observation that there's some advantages to using level sets instead of graphs to represent functions. This is my first example, which I think is very dramatic. Here is a function for which we simply cannot draw the graph. I mean, if you hang your hat on looking at graphs of multivariable functions and say, you know what, I'm gonna make it through Math 212 understanding things only from the point of view of graphs, because that's how I'm accustomed to thinking, right? You don't have an option here, right? I mean, this is a loser. You can't graph this function. Be a 4-dimensional picture, right? You can, though, take this function, right? Function of 3 variables, and draw level sets. Now, here's some level sets. Right? They're spheres of various radii centered at the origin. And so this is a picture that hopefully we will be able to do something with. The calculus of the function that we're interested in studying hopefully will have something to do with these pictures, and it will. So very importantly, we have to realize here we are not looking at a graph. Right? This is not a graph. By the way, I know y'all have all kind of gotten away with a certain sloppiness of language in high school, possibly even single variable calculus courses here at Duke, to just kind of interchangeably use the word graph with the word picture. So you have to really nip that in the bud now. Make every effort you can to not do that, because the distinction is important. Not all pictures are graphs. Okay. All right, so there's some other things I want to observe about level sets. We're almost done with the section on level sets, but some neat facts. Any equation. There's a broad start to a statement. Any equation, right? Its solution set can be thought of as a level set of a function. Now, this is not a hard observation. This is an observation I've already made, in fact, that if you have an equation, stuff equals other stuff, you can just take the stuff on the right and subtract it over to the left-hand side, and the result is stuff equals 0, right? Which is some function equaling 0 means you're setting it equal to a constant, and it's a level set, right? So algebraically, this is not hard to see. But this is a really important fact to observe, because, following observation, if you want to understand an equation, which very often we do, right? Calculus might be interesting, might be a tool, might be a useful tool somehow in understanding that solution set to that equation. Calculus involves, let's say, for example, derivatives. Maybe something about the derivatives would be useful to understand this set. You take derivatives of functions, right? So if you want to get calculus involved, this solution set to an equation, we have to somehow relate it to a function. What this says is you can always relate any solution set, any equation you might be interested in, you can always relate it to a function, thus giving you access to the tools of calculus in ways that we have not yet determined by way of the level set construction. That's awesome. Right? That's not true about graphs. Right? Not every solution set to an equation can be viewed as a graph of a function. Easy counterexample is a circle. Right? X squared plus y squared equals 1. That is not the graph of a function. Right? Because it fails the vertical line test. I hope you all remember the vertical line test. Right? So here's a vertical line, and look, it hits twice. So failure of the vertical line test. That is not the graph of a function. So you cannot relate every equation to a function by way of graphs. But you can relate every equation to a function by way of level sets. So if we can understand the calculus of level sets, we have a powerful, always applicable tool for understanding equations. Okay. All right. Related fact. All graphs can be viewed as level sets. Now, again, this also not true. Not every level set can be viewed as a graph, but every graph can be viewed as a level set. This is another advantage that level sets have over graphs. Again, sort of more general. If you're dealing with a graph, you can always say, you know what, let's view this instead as a level set. It's always an option, in other words. Now, the reason why this is true is pretty straightforward. If you're viewing a graph of some function f, there's the equation that describes a graph. Notice that equation is, it's logically identical to that equation. I just played the trick that we just talked about. I took the right side, moved over to the left side with a minus sign, right? Trivial. Algebra 1 move there. So these are logically equivalent equations. And notice what this is. Here we are clearly looking at a level set of this other function. Right? Level set because something equals 0. Yeah. So when I write the equation this way, y equals, that's what makes this a graph. When I rewrite it so that stuff equals 0, that's what makes this a level set. Okay. Now, very important to recognize these are different functions. The function whose graph we're looking at, the function whose level set we're looking at, different functions. Right? They better be because they relate to the same set by way of different constructions. So let's emphasize how different these functions are. The function whose graph we're looking at has this formula f. It has n input variables. Right? The function whose level set we're looking at is this function g. It has n plus 1 input variables. Right? You can see right there in the formula. It's in order to compute what this function I have in purple called g, I need to know x1 through xn. That's n variables, but I also need to know y. Okay. So don't make the mistake of sort of sloppily interpreting this statement as saying a graph of f is a level set of f. It's not. Of course not. Right? But a graph of f is a level set of a different function, g. Okay. Any questions about this little move here? Okay. This is a deceptive trick. I'm going to call it deceptive observation because you look at the algebra involved here and you think, all you got to do is just take the thing and move it to the other side of the equation. This is algebra 1. It's trivial, right? What makes this challenging and what y'all need to be taking seriously is that this is a statement that requires, to be interpreted correctly, a strict interpretation of the terminology. Right? You have to make the exact correct interpretation of what we mean by a graph of a function. You have to make an exact right interpretation of what we mean by a level set of a different function. And interpreting those strictly, then yeah, the actual algebra involved here is trivial, right? But don't underestimate the interpretation aspect of what's going on here. Okay, so that's all we had left to do with section 2.4. So we're now done with 2.4. We're going to move on to 2.5, parametric curves and surfaces. This is the language involved in this construction is it's kind of backwards in a way. So we'll talk about that in a moment. So what I want to talk about first is this thing called the image of a function. And you already know what that is. The image, I wanted to switch to green, I'm sorry. The image is this set right here. It's a set of actual outputs from the function, right? So we distinguish between the image and the target. The target is just, RM, just what kind of critters come out of this thing, right? Well, points with m coordinates are the kinds of objects that come out of this function, so that's the target. The image, though, is precisely exactly which points in RM come out, right? So anyway, that is a set. It's a geometric object. Sometimes it's an interesting geometric object. And so this is a way that, from a certain point of view, the image can be thought of as a construction. There's a geometric object, a picture of sorts, that directly relates to a function. Okay. Alrighty. So observation to be made. Notice that the image lives inside of the target of the function. Right? So let me remind you, level sets live in the domain of the function. Right? Level sets are collections of points in the domain that satisfy a certain property. The image lives in the target of the function. So it lives in a different world, representing the function in a different way. Okay. So what kind of a set is it inside of the target? I'm going to give you an example. Let's suppose we have a function from R1 to R2. This is an easy starter example. So here's our input axis. I'm going to call the t axis. So t goes into this function. X and y come out of this function. And let's draw what the image would look like. Here's f. What does the image look like? Well, this input value of t and give rise to some point in the target. The next value there of t is going to give, some other point in the target. You can kind of keep going. That point may go to that point. And then let's see, that point might go there. And that point goes there. And I appeal to your intuition about what's going on here. As we move along the t-axis, right, as these input points move, the output point is going to move through space. So what you would expect to happen, looking at the image, you would expect, for a function from R1 to R2, you would expect the image to be a curve in R2. A curve in the target. Is everybody on board with that? This is just a kind of a geometric appeal. I'm not proving anything here. Seem plausible? I'm going to show you several examples where this actually bears out. Okay. All right. Okay, so, yeah, let me come back up to this picture then. Yeah, sure. Okay, so this curve here is called the image. Here, I'll put the whole thing in quotes. The image of the function f. So you give me a function f. Image says produce this corresponding curve. The language I claim that I want to talk about next is kind of backwards. It's not you give me a function, I give you a picture. I want to talk about suppose you give me a picture. Suppose you give me a curve. And I ask, what is the corresponding function? Sort of go in the other direction, if you will. And that language is, we say that this function is a parameterization of the curve. And I'm going to call the curve C. Let me stick a label. We'll call this curve C. So the curve is the image of the function. The function is a parameterization of the curve. Everybody see what I mean by kind of backwards? Grammatically, if nothing else, grammatically kind of backwards. Okay. All right. So let's see some examples. Here's a function. And I'm going to start with a lot of examples along the lines of, here's a function, what's the corresponding image? And we'll talk in a little while about, well, suppose somebody gives me the image. How do I find a parameterization of that image? We'll come back to that. So here we have a function given. F of t is t plus 1, comma 2t minus 1. Now that's a function from R1 to R2, just like the example we were just talking about. And I pose the question, now what is the image of this function? Well, you could, I suppose, start plugging in values of t. Right? Plug in one value of t, plot a point. Plug in another value of t, plot a point. Like we were doing with colors up here. But there's a lot of values of t. There's infinitely many values of t. We don't have that kind of time. Right? So let's try to think of a better alternative. The better alternative is to notice that these outputs themselves are functions. That t plus 1, here, let me do it like this. This t plus 1, that's the x coordinate of the output. This 2t minus 1, that's the y coordinate of my output. They're both functions of t. Maybe I can find a way to relate them. If I can find a way to relate t plus 1 and 2t minus 1, then I, in effect, have found a relationship between x and y. Namely, I found an equation, which is a great way to represent a curve. It's sort of a great alternative way to represent a curve. So can we find such a relationship? Now, how do you find a relationship between these two functions? It's not algorithmic. It's by hook or by crook. Try to be smart alecky about it. Anything you can dream up. What can I do, for example, to t plus 1 to make it turn into 2t minus 1? And I propose, well, hey, let's take t plus 1, let's multiply it by 2. Now it's 2t plus 2. That's pretty close. Oh, but I don't need 2t plus 2. I need 2t minus 1. So let's subtract 3. Anyway, play around with the algebra, right? Fiddling around with it like I was describing there. And it's not hard to persuade yourself that y is 2x minus 3. That's an equation. It's an equation of a line. It's the equation of this line here. And I claim that that is our image. Yeah? Everybody on board? So it's kind of how these things proceed. Now, there is a worry that we might bring up. Okay, technically what I've shown here is that every point that comes out of this function satisfies this equation. That means every point that comes out of this function, the entire image of this function is on that line. That does not necessarily mean that it is the entire line. Right? How do I know that every point on that line comes out of this function? Right? Well, this is just a matter of sort of direct calculation you can just solve. If you give me a point, here, let me zoom back in so I can see the algebra here. Look at this formula here. X is t plus 1. I would like to know that there is some value of t that will produce a given point, x naught, y naught. How am I going to find that value of t? Solve for t. Right? This suggests t should be x naught minus 1. And if you take this value of t and plug it in to that function, sure enough, the point in question comes out. So any point that satisfies this equation, any point on this line, definitely is an output from this function because there's the value of t that does it. Okay. So anyway, this is usually not a worry. I just wanted to point out that this is this is a worry that can be dealt with, and that's how you deal with it. All right. Let's look at this one. Here's another function. Now, this is a completely different function. I mean, really different function, right? Look, it's got cubes in it. The last function we were looking at was, it had only constant terms and linear terms. And so this is a really different function. Looks a lot harder in a way, right? Still a function from R1 to R2. So this is still got an image that we expect to be a curve. Well, here's the thing. Notice that our x and our y, still functions of t, I can still kind of fiddle with them and try to figure out some relationship between them. What can I do to the x to turn it into the y? Or what can I do with the x and the y together to come up with some equation? Can I combine x and y in some way to get 0, perhaps, or something like that? And you find, without too much trouble, that they still satisfy the same equation as the previous example. That's weird. Right? This very different function parameterizes the exact same line, or said differently, this very different function has exactly the same image. Yeah? Everybody on board? So this is one of the downsides of using images to understand functions. They are not unique to a given function, right? A given curve could be the image of lots of different functions. Or let me say that the other way. Let me say that grammatically backwards. For any given curve, there are lots of parameterizations. Right? Here being an example of a line with, we've seen now, 2 distinct parameterizations. Okay. All right. So to sort of help out with this awkwardness, I want to give you a different point of view on how to think about parameterizations. And that is, I want to encourage us to start thinking of these functions whose images we're looking at. Let's think of them as giving position as a function of time. Now, I didn't talk about that point of view previously. I just said, well, for a given input value of a variable that perhaps arbitrarily I called t, right? What is the corresponding output? Input, output. That's all we were talking about. So now I want to introduce the perspective, and this is just a way of thinking. This is not law, right? But a very convenient and useful way of thinking is, what if we viewed t as representing time? If t represents time, then the parameterization represents a movement along the curve. You might think of it as it represents a process by which you trace the curve. Right? And so with that point of view in mind, what's the difference of these two parameterizations? Well, here we have one parameterization of that line, and then here we have a different parameterization of the line. Said differently, here we have 2 different ways to trace that line. Yeah, okay. That's not that weird anymore, right? The fact that there are multiple parameterizations boils down to, if you have a line, there's different ways to draw the line. Right? And I point out that you can emphasize the differences in those 2 ways by putting little check marks on here. Think of position's a function of time. Let's note certain positions at certain times on the picture. Right? As we draw the picture, you can say, here's where I am at t equals -1. Here's where I am at t equals -0.5, etc. Just going along. And notice this collection of checkpoints, you might call them, very different from this collection of checkpoints. Let's think about the process of moving along these 2 different lines. Whoops. Okay, I hit a button there. Sorry. Between t equals -1 and t equals -0.5, in this one drawing, I only went that far. In this other drawing, I went further. Right? So this represents the differences in these 2 tracings of this line. You might say, this line we traced at kind of a constant speed. We'll be able to make that precise later. Geometric appeal for the moment. And this one, we did something weird. We started off moving really fast, and then we kind of slowed down, and then we kind of sped up again at the end. So, same line, different ways of drawing them. Just another metaphor you can run with. I don't know if what kind of snails were around when you were growing up. When I was growing up, after a rain, there'd be snails all over the place. And the snails, you could tell where they'd been because as they oozed along, they leave this trail of slime. Anyway, I don't know if y'all are familiar with that. It's hopefully you are. If you're not, that's how snails work, or some snails anyway. So the curve is the trail of slime. The image, you might say, is the trail of slime left by the snail, right? Whereas the parameterization is the process of the snail moving along, leaving that trail of slime, right? So along those same kind of metaphorical lines, you can distinguish between a curve and a parameterization by it's the difference between a road and a road trip, which I don't know, I find amusing as an example. But of course, there's a big difference between a road and a road trip, right? Like I-40 sits there. I-40's been there for a long time. It doesn't do anything. It's there, right? It's a static thing. A road trip is, hey, we get in the car and we start driving on I-40, and we're moving fast, and then we see a cop and we slow down, and then he leaves, and then we speed up again, and then we decide to stop for a moment, and we're going to go in and get a soda to drink, right? And then we get in the car and we go again. There's a whole process of where you are as a function of time as you drive along the road. The road's not moving, we are. Does everybody see the difference? All right. I'm going to use that particular metaphor a lot, the road versus the road trip. So a bunch of examples. I don't have time to do all of the examples. Again, that's typically going to be the case. I won't have time to do all the examples. It doesn't mean they're not good examples, but just that, I have to be picky and choosy about how I use time in class. So I'm going to skip this example, but I encourage you to look at it because something really interesting happens in this example. So give this one a look. Likewise, all the other examples I skip. Here's one. Cosine t, comma sine t. What does this parameterize? Let me write this down a little bit differently. If x is cosine t, and if y is sine t. What does that trace out? What road trip? Or this road trip? What road am I driving on in this road trip? You might say. Okay. So again, you want to look for relationships between these objects. Let's remember the Pythagorean identity. Remembering that cosine t is x and sine t is y. What we have is that every point on this road trip satisfies that equation. X squared plus y squared is 1. This traces out the circle. So this is a parameterization of the unit circle. Yeah? Pretty good? Okay, here's a harder one. Here is a parameterization in R3. So there's 3 coordinates now. X is cosine t, y is sine t, and z is just t. Now, how are we going to get our hands on this? Right? Can I come up with some sort of algebraic relationship between these? That we can do the whole Pythagorean thing, but then what does that have to do with z? How do I get z involved? It's not clear that I'm going to be able to use the previous trick, right, to figure this out. So, like I said previously, this is not an algorithmic process. It's not always do the following and it'll work out. There are just different things that you can try. I'm going to show you what I think works nicely in this case, and that is to think of this curve in 2 different ways. On the one hand, let's think about what does the shadow in the xy plane look like. Let's think of the projection down to the xy plane. All right, so the curve is doing who knows what, always casting a shadow, a projection down in the xy plane. Let's just try to understand that projection first. In other words, let's just look at the x and y coordinates. Well, these x and y coordinates, we've already understood that's what the x and y coordinates are doing. They're going around in a circle. Yeah. Now, having understood that, next question, what's the z coordinate doing by itself? Well, that's easy. Z is just increasing with t because z is t. Right? So you can put these two pieces of information together. I know this. So this curve that I'm interested in, I know that its shadow down in the XY plane is doing this. Right? It's going around in a circle. And I know that the height is increasing at a constant rate. And so geometric appeal is making a helix. Okay. So this picture here. So we came to this conclusion by way of a pretty different method, right, than what we did with the previous example. Something to keep in mind, right? I mean, sometimes this is the kind of thing you have to do. Okay, here's yet another different one. Here's a parameterization of something. X is t minus sine t, y is t plus sine t. Well, you can play around and try to come up with relationships between x and y. It's surprisingly hard to eliminate t. I mean, it's doable. But it's not immediately clear how you would go about eliminating t from this equation. And in the way that you can do it, you end up with something that's still kind of hard to algebraically make sense out of. So it's kind of a hard problem. So let me show you a different point of view, and that is to take your parameterization and rewrite like that. Just algebraically looking at it, notice that there's kind of different categories of terms there. There's the non-trig terms and there's the trig terms, and it just, if you separate them out like this, then you can interpret these as in different ways. You can interpret this as that's a really easy curve to understand. T comma t, that's just moving along the line y equals x. That's an easy one. That's moving like that. This is, there's an oscillation happening because you see that sine t there, but it's an oscillating factor times a constant vector of -1, 1. And -1, 1 is an easy vector to draw. -1, 1 is, something like that. Right, there's -1, 1. Let me put it in a box instead of that. -1, 1. And what this says then is as time passes, as t increases, as the green point moves along the line y equals x, I'm going to be adding to that an oscillating multiple of -1, 1. Right, so think of the green as a moving point, and think of the blue as a vector whose direction is always -1, 1, but whose where the scalar factor of sine t is being multiplied. So you get these blue vectors. As time passes, that factor sine t increases, and then it decreases, and then it becomes negative. Right, like that. So blue plus green all together gives me the total curve just like that. Everybody see the argument there? Now this is, again, totally different. This is not like the way we understood the helix, and it's not like the way we understood the circle. They're all different, right? So by hook or by crook, different tricks for different situations. So all I can do here is add to your toolbox of tricks for analyzing these things, and then you have to figure out, appropriate to each example that you are faced with, which tools best apply to that situation. Okay. All right. Okay, let's talk about parametric surfaces. It's a very similar idea. Here's a starter example. Here's a function you'll notice from R2 to R3. And so there's three outputs, just like the previous examples, or at least one of the previous examples. 3 outputs. But now there's 2 inputs. So let me note right off the bat, this idea of thinking of position as a function of time, out the window. Right? We don't have 2 time variables. So we kind of have to return back to the idea of, well, we're thinking of position x, y, z simply as, well, these are just outputs from some function that has two different inputs. Okay. Now, geometric appeal, what kind of thing would I sort of expect that I get if I have two inputs go into a function? What kind of geometric object should I expect to come out? Well, let's see here. Let me start with, I'll start with blue. So that point, going to have some output. This point next to it's going to have some output. This point next to it's going to have some output. And you can, persuade yourself as you move along here that as you go that direction in the domain, you're going to get some sort of a curve, sure, right? But this is not the only direction you can go in the domain. There's also this other direction. There's, let's see here, that point is going to have some output, and that point is going to have some output, and that point, whoops, sorry, I missed, orange. That point's going to have some output, etc. So as you go along this way, you're going to get a different curve. Right? And then, you can kind of start filling in between this point it's not exactly in the horizontal direction, not in the vertical direction. You would sort of expect that to end up with a point there. And, filling in the blanks, nearby points expected to go near to the images of their nearby inputs. You would sort of expect this two-dimensional domain to create a two-dimensional output. Namely, you would expect the output to be a surface. Just a geometric appeal. Good news, this is actually mostly what happens, right? So this is a geometric appeal that leads you in the right direction, right? But I'm not going to try to prove this in any rigorous way. But that is what happens. Okay. All right, so back to this example, what kind of a surface do we get with this? Again, function with two input variables. Well, again, that's x, that's y, that's z. We have various tools that we can try to use to understand this, and a pretty convenient one is to try to find a relationship between the x, the y, and the z. Not hard to persuade yourself that z is 2x plus y. That's just algebra. And of course, z equals 2x plus y is the equation of a plane. Right, so this function here is a parameterization of a plane that, kind of hard to draw that plane, but it's a plane that's goes through the origin and it's kind of angled, kind of up, coming toward us out of the page. Okay. All right, so this is called a parameterization of the surface. The surface is the image of the function. The function is a parameterization of the surface. Okay. Here's another one. What's the image of this function? Again, two input variables, phi and theta. Three output variables, x, y, and z. What do these outputs actually look like? You might notice this looks an awful lot like the spherical coordinate formulas that y'all have either memorized or nearly memorized. Hopefully this at least looks familiar. Right? In fact, if you were to stick a 1 in front of each of these, then with rho equals 1, this really is spherical coordinate. Oh my gosh, what did I... Oh, I think I touched that with my elbow. That was my bad. That was not their fault. That was my fault. So with rho equals 1, this is exactly the formula for spherical coordinates. So what we have here is a bunch of points that satisfy the equation rho equals 1. This is a bunch of points on the sphere, the unit sphere, with the equation rho equals 1. And you can persuade yourself without too much trouble, thinking in terms of spherical coordinates, that, well, look, phi and theta can be any values. And so, in fact, this traces out, this parameterizes the entire unit sphere. Okay. Okay, so now I want to go the other direction. We've been talking about, here's a function. How can I figure out what the image is? Now I want to say, suppose I have a curve that is thought of in some way. Maybe I have an equation for it. Maybe I understand it in some other way. Suppose I have a curve. How do I find the parameterization? How do I find a function whose image is that curve? Okay. So I have a strong favorite trick for how to do this. It's what I like to call the graph parameterization. It's a really slick move. Here's the move. Suppose you have a graph. So here's a curve, right? That's a graph of a single variable function. Now, remember, graph is a very specific thing. Graph does not mean a picture, in some way related to the object I'm interested in. This is a specific construction where y is f of x. This function f being a single variable function. Okay, so I have a curve understood now as a graph. Because it is understood as a graph, because I know that y is always f of x, the move on the parameterization, and it's really very simple, but it's very slick, is go ahead and just let x equal to t. Having let x equal to t, okay, well, wait a second. If x is equal to t, plug that into there, that kind of means that y has to be f of t. Y has to be f of x is t, therefore y has to be f of t. And notice that what you've got then is a parameterization. Here it is. T comma f of t. That is a parameterization of this graph. That you can, in fact, directly check this y, f of t, is f of this x, t. So it works. Right? Very simple move, right? But very powerful in that you give me any curve thought of as a graph, and this will parameterize that curve. So I hope y'all will really digest and absorb, and for sure make sure that you get this comfortably in your toolbox, because this is the best trick that I know for how to parameterize curves. Okay. Similar deal to parameterize a surface. If you have, here we go. If you have a surface that is a graph, well, I mean, z is what that means. If you say this surface is a graph, that means z is a function of x and y. That's what graph means. Graph means we're setting a function equal to a new variable z. Okay, well, if z is f of x, y, go ahead and make the choice that we're going to let x and y be u and v. And having made x and y u and v, well, wait a second, you plug that into there, and that pretty much means that z has to be f of uv. And there's your parameterization. U comma v comma f of u comma v. So this is a graph parameterization of a surface. Again, great trick. Really cool. And by the way, this particular situation of here's a surface and I need to parameterize this surface is going to be huge in Chapter 6 later in the course. When we get into what we call vector calculus, parameterizing surfaces and also parameterizing curves is going to be a very big deal. So this is the main trick that you're going to use at that time, graph parameterization. Okay. All right. Now, let me point out that arguably the big trick here is, I presented this as, the big trick is that we're looking at a graph, but let's break this down a little bit more generally. What I'm really using is that one of the variables is a function of the other two. And there are other situations where this happens that, you might not think of as graphs. So, for example, Let's look at this example here. Suppose I can view R as a function of theta. Now, I guess you could say it's a polar graph, but look, if we don't think of it as a graph because it fails the vertical line test, right? Or it certainly could fail the vertical line test. But if R is a function of theta, notice you can just take that and plug it in to your plain old regular polar coordinates formulas. X is R cosine theta, Y is R sine theta. And what comes out gives you position as a function of one variable. Right? X, namely x comma y, is a function of theta. So that's a parameterization. So it's not exactly. It'd be weird to call this a graph parameterization because again, these curves are not necessarily graphs, but it's like the graph parameterization in that, well, it's morally the same trick that we're taking advantage of the fact that one of the variables is a function of the others. I guess you could call this a polar graph parameterization, right? Be a reasonable choice of terminology. Okay. There's an example along these lines with spherical coordinates. Suppose rho is a function of phi and theta. Well, take your plain old, regular, good old spherical coordinates formulas and then just plug in rho in terms of phi and theta, and then the rho disappears, and again you have position x as a function of just phi and theta, thus giving you you might call it the spherical graph parameterization of this surface. Everybody see that move? Feel free to ask a question. Is everybody happy? Okay, so just as a for example, suppose we have this equation here. So there's a spherical equation for some surface. What does that surface look like? Wow, I don't know. Hard to figure. Right, that's we could come up with something. We'd have to really think about it. Rho is approximately 3. This is some sort of a lumpy sphere, you might say. It's a lumpy variation on a sphere anyway. But exactly how would I draw that? I don't know. That's tough. How would I parameterize it? That's easy. Rho just goes right in there. And simply writing down position is the usual x, y, and z are the usual functions of rho, phi, and theta. Now I have position as a function of only phi and theta, and I have a parameterization of my, I can't even imagine what that thing looks like, surface. Yeah? Everybody good? All right. Sometimes it might not leap out at you that you have one of the variables as a function of the others. Let's look at this equation here. That's a nasty looking equation. My gosh, there's a z cubed. There's an e to the xz. Right? Nasty. Now, how would I parameterize this surface? Seems impossible. I can't even understand what this surface looks like. Now, I can try to start to solve for one of these variables in terms of the others. It's going to be really hard to solve for x. Notice x is inside the exponential and also outside the exponential. That makes this a transcendental equation, and we can't solve for x. Likewise, we can't solve for z because it's inside an exponential twice and outside an exponential. So, forget solving for z. But we can totally solve for y, and that's just downright easy. Y is a function of x and z. Play the same trick. Namely, let x and z, so let x and z be u and v, and then y is what it has to be, having solved for it in terms of x and z. And parameterization. So, neat fact, you can parameterize stuff that you can't even draw. All right, is everybody good? All right, a bunch of exercises. Now we're going to go through and hopefully actually finish section 2.6 as well. the way I'm going to finish 2.6, which is a long section, in 25 minutes is by skipping most of it. This is a standard choice. I always do this every term. The purpose of this section is mostly just to give you a bunch of examples to look at. There's not really a lot of new material in this section. So I'm going to talk about the one idea that's kind of, dare I say, new. It's not even all that new. And then I'm going to do a couple of the examples, and the rest of the examples in this section are for you to read and study at your leisure. So I encourage you to do that. I think they're all good examples. I think it's all good learning material. So give that a look. So let me remind you of the vertical line test. Right, this curve here passes the vertical line test. Every vertical line intersects the curve exactly once. Whereas this curve here fails the vertical line test. This curve does not intersect every vertical line exactly once. It intersects this vertical line 3 times. Right, now the fact that it intersects certain lines only once is not enough. Right? It still remains, this has failed the vertical line test with at least one line, and therefore this is not a graph. Yeah, everybody on board? Everybody remember this from hopefully Algebra 1 or Algebra 2 or some distant way back. So I just want to observe there's a similar statement that you can make about surfaces. If you want to ask the question, is a certain surface a graph? And when I say graph, I mean in this case I mean graph where z is a function of x and y. So this is kind of a normed. We typically make the output variable the vertical axis. You could, I suppose, consider a sideways graph where y is a function of x and z. Right? But let's just talk about this point of view here. And this surface as drawn passes the vertical line test everywhere. This is a graph. This surface over here, as drawn, fails the vertical line test. This is not a graph. Right? In other words, I cannot have z be a function of x and y, because if I did, that value of f of x comma y would have to be 2 different numbers for this x comma y. And a function cannot take 2 different values. Okay, so that's all the new material in this section. Everything else is just examples. So I'm going to go straight to one of my favorite examples here. And let's think about this line in R2 that passes through these 2 points, 0, -1, and 1, 1. So that's this line right here. Think about different ways that I can represent this. Now, flashbacks to Algebra 1, right? I know y'all know how to represent, with the equation of a line, right? But what I want to do specifically now is talk about the different functions that we can connect this to. I know y'all can write down an equation for the line. That's Algebra 1. But what functions can we relate to this line, and specifically by which construction do which functions relate to this line? So is this line a graph of a function, and if so, exactly what function? Is this a level set of some function, and if so, exactly what function? Is this an image of some function, and if so, exactly what function? So I want to just show you that there's answers to all 3 of these questions. The answers are all yes. This is a graph, this is a level set, and this is an image. In other words, it can be parameterized. So there are 3 different functions with 3 different, calculi. There are 3 different functions whose calculuses are totally different, right? That in those different ways represent this exact same line. Okay. So very important to be able to identify what those functions are. Now the equation of the line is pretty easy to write down. Let's see, where did I do that? Yeah, here we go. Y equals 2x minus 1. So there's the equation. Right? The equation is not a function. So, question, what is this a graph of? Okay. Well, I'm looking for some function that when I set it equal to y, gives me that equation. Right? This is what it means to be the graph of something. Right? If you're looking at the graph of f, you're going to set f equal to y in this case, and I want the result of having done that to give me this line, namely to give me the equation y equals 2x minus 1. So, what function is this the graph of? Well, you can read it right off the page. F of x is 2x minus 1. Right? So we have here f from R1 to R1. There's one input variable, one output variable. This function, f of x equals 2x minus 1, its graph is this line. Is everybody happy? Everybody on board? Now I want to emphasize one thing here. I know that the algebra that happened here is really trivial, right? Again, so that's not the point to this discussion. The point to this discussion is not to, can you accomplish the trivial algebra? The point to this discussion is, can you identify the correct function, making an appropriate understanding of the word graph? Can you demonstrate the process of knowing what a graph is? Graph taking a function and giving you a curve, an equation for a curve. So what's very important in that is that you write it correspondingly. So in other words, you have to write the function like this. You have to write it as a function. It happens every year that students, to the question, is this line the graph of some function? A lot of students will write down, yes, the graph of this function. It's not a function. That's an equation. That's the equation for the line. Here, very critically and importantly, we're looking for a function that, when you set it equal to y, gives you this equation. I'm not looking for the equation that resulted from setting it equal to y. Does everybody see the difference? It's a really important difference. So make sure that you interpret the question appropriately. If the question asks you for what is the function whose graph is the line, give me the function. Right? This is worth very little in a question like that, because again, getting to this right here really is algebra 1. Right? Okay. All right. Next question. Is this a level set? Okay. Is there some function g, we ask, is there a function g such that when I set it equal to some constant, and I'm going to say 0, no particular reason, you don't have to, is there something that when I set it equal to 0 gives me an equation equivalent to that? Now this one's not quite as immediate. The equation up there doesn't just line up perfectly with y equals. Right here we have 0 equals there, but I can certainly take this equation and rewrite it very conveniently as 2x minus y. Oh, well, sure. Anyway, let me do it like that. Right, there's a equivalent equation, and now these line up just fine. Right? So I would be perfectly within my rights to say that yes, we are looking at a level set of that function. And what I did here in the book, arbitrarily I subtracted the other direction and got, this is of course just as equivalent, y minus 2x plus 1, morally equivalent, giving me that function there. So is this line a level set of a function? Yeah, it is. It's a level set of this function. Note that this is a function from R2 to R1. Right, so this function has two input variables, x and y. There they are. You can see them right there in the formula. It has one output value. That one output value is, well, the formula. It's y minus 2x plus 1. We're good? Everybody happy? Okay. All righty. Last, can I parameterize this line? So there's lots of different ways that you can parameterize the line. How do you parameterize the line? One thing you could do is you can use the graph parameterization. Right? We already know it's a graph. It's a graph of that function. You could use the graph parameterization. Boom. There's your parameterization. What I did here is I used Chapter 1 methods, and I observed that, well, I know that I have a point, and I have a vector parallel to the line, and I'm going to use Chapter 1, x naught plus TV to parameterize the line. So take your pick, either way, and here's the result of one of those. That is a parameterization of the line. Oh. Everybody on board? Okay. Notice that these three functions are all very different functions, different domains, different targets, different formulas, completely different functions, which, by way of three different constructions, describe the exact same line. Exact same line. Okay, with the exact same equation. Okay, so let me just note for the record, I think this stuff is really important. I've seen over the years lots and lots of students who just crash and burn at a certain stage in Math 212 because they understand that the calculus of a function whose level set is the object that we're interested in relates in a certain way, but the thing is they're applying that to a function whose graph is the surface that we're interested in, and of course it completely makes no sense at all. Right? So there's a lot of square peg round hole stuff that ends up happening inadvertently because students are generally kind of sloppy about, well, are we looking at a graph of something? Are we looking at a level set of something? So this is not viable, right? So make sure that you don't be that student. So make sure you understand the difference between these different constructions and the different resulting functions. And then when we start talking about the calculus, make sure you categorize the interpretations appropriate to the venue. Yeah.
Was there a particular reason you picked the parallel vector to be passing through 1, 2?
If memory serves, I'm guessing that I came up with this parallel vector 1, 2 by subtracting 1, 1 minus 0, negative 1. But there's different ways. I mean, if you wanted to, you could have figure out where that intersection point is and subtract like that. I don't know. It doesn't matter. Yeah, any parallel vector will do. Yeah. Okay, so there's another example. Similarly, this though is a plane, and we can view this plane as being a graph. We can view it as being a level set. We can view it as being an image, namely we can parameterize it, and again by three different functions. So I'm going to let you all read this example. I think it's just as important as the previous one, sort of one dimension up. And give that a look. Make sure you're comfortable with this kind of thing. By the way, as y'all know, all my midterms are public, right? They're on a website somewhere, and y'all have access to those. And so y'all will notice this on your own anyway. But I'll go ahead and reveal here. I have given many midterm questions that say, here's a plane, or here's a surface, here's a geometric object that I describe in some way. What function is this a graph of? What function is this a level set of? What function is this parameterized by? So, anyway, in B. Okay. Okay, so there's, like I say, a bunch more examples in here. I do want to do one more, at least part of, and this is a bicycle example. This is an example that uses the vector addition tool that we talked about previously. And so here's the idea. We've got a bicycle wheel here, and the bicycle wheel has an axle right in the middle, as of course it should, and it has a reflector kind of halfway in between the axle and the tire. The question is, as this wheel starts rolling, what path does the reflector follow? And I don't know if y'all have ever noticed, but as it's dusk, or nighttime or whatever, and if somebody's riding down the street on a bicycle, the street light hits the reflector, and that reflector ends up doing something kind of like that. Y'all ever notice that? Okay, we're going to try to describe that curve algebraically. Now, it would be very hard to find an equation for this curve. That's hard. It's in other words, can we view this as a graph of something? I don't think so. Can we find this? Can we view this as a level set of something? I don't think so. It turns out that it's not that bad to parameterize this curve, though. And the vector addition is the big trick. So first observation I want to make is as this thing moves along, the axle is really easy to describe. The axle just does that. Right? The axle is always the same height off the ground. As the bicycle moves, there it goes. Right, so it's real easy to parameterize that. Now I'm going to parameterize that axle in terms of, not in terms of time. I don't want to have to worry about how fast the bicycle is going. I want to parameterize in terms of this angle theta. I'm going to parameterize in terms of that angle theta there. That represents how far the bicycle has turned, right? And it's just more convenient to do it this way because you can see as the wheel turns, as that angle theta increases, then that affects the geometry of what happens, and it's just immediately connected to the things I need to relate to. So in this case, the observation is, well, that angle theta is the same as this angle theta. The distance traveled is the same as that arc there. Now this is a physical appeal. Best way I have of describing this physical appeal is that the amount of rubber that has touched road is the same as the amount of road that has touched rubber. Right? In other words, there's no slipping. Presumably, this is a nice dry road, no slipping. Right? So when something is moving like that, right, if there's a non-slipping motion of the tire along the road, the amount of road that let me document on the picture as it goes. The amount of road that has touched rubber is equal to the amount of rubber that has touched road. Right? So the distance, in other words, that this A has moved is the same as that arc. And high school geometry tells me that arc length is radius times theta, and that gives me then this formula here. Yeah, everybody happy with that? Okay, now that's where the axle is. That was not the question. The question was, where's the reflector? Well, gosh, the reflector it's close to where the axle is, but there's a difference. The difference is that difference vector there. So you might say the reflector's location minus the axle's location. And that red difference vector is doing something pretty straightforward. And that red difference vector starts off like that, and then just kind of goes around in a circle. Right, now keep in mind, I'm not talking about the arrow. The arrow that starts at the axle, ends at the reflector. That arrow, as the bicycle moves, that arrow is kind of going along with the bike, right? But arrows are just ways of representing vectors. The vectors don't have locations. So I can just as well represent the vector that this arrow represents with that arrow that I'm, for my own convenience, going to leave its tail at the origin. Right? So as the bicycle moves along, this red vector is going to just kind of go around in a circle, like so. So sines and cosines, right? Pretty straightforward sines and cosines. Yeah, how we doing? Everybody happy with that? Now a couple of details to worry about. We know that this angle is theta. We know that this distance is, okay, well, wait a second, what is that distance? The distance between the axle and the reflector, got to go down to the statement of the question, the distance between the axle and the reflector, well, let's see, it's half of the way from the axle to the tire. It's half of 16, so that distance is 8. So that distance there is 8. And it's going around in a circle. Now, wait a minute. It's going clockwise, not counterclockwise. Be careful as you, when you write down this parameterization. This is not going to be 8 cosine t, 8 sine t. That would be going that way. We're doing the opposite. We're going the other direction. That means that even though the x-coordinates are the same, the y-coordinates are opposites of each other. So it's 8 cosine t negative 8 sine t. Theta. Sorry, I meant theta. Theta. Yeah, everybody happy? Okay, so that gives me that. So the axle is doing this. The thing that I add to the axle to get the reflector is doing that. Add them up. That plus that gives me that, and that's the position of the reflector. Everybody see how that works? Okay, so there's an exercise at the end of this section, which, by the way, I'm declaring us done with this section now. There are other examples in here, but these are all examples I'm going to ask you all to read on your own, and they're all good examples, right? But again, we just don't have time. So there's one exercise that continues along with the bicycle application. So FYI. And let's see if I can find where it is. Yeah, here it is. So we have another path of the reflector on the bicycle, different variations. So what you're going to do is you're going to take the ideas that we just talked about and tweak them just a little bit as you go along to get the answers to these 4 different variations. Note, however, this one is no longer assigned. That very last one. So you might have noticed that the questions that are on the exercises that are on the syllabus are usually almost exactly the same. They're usually all of the questions at the back of the section. Not always, though. Some of them over years, I have removed, and this part 4 did get removed some time ago. So you don't have to do that one. On the other hand, if you're looking for a challenge, something to try. Okay. One last announcement to make. I do have a minute and a half left. The next section is limits and continuity. We are actually pretty significantly behind schedule at this point. Limits and continuity is a good opportunity for us to make up for a little bit of lost time. So what I'm going to do is I'm going to actually skip this section for the moment. It's not exactly quite prerequisite for the stuff that we're going to be doing next. So we can get away with delaying it. What I'm going to do is I'm going to assign this as a video to watch over the weekend. So, of course, we have videos from past semesters, and I'm going to ask you all to watch the appropriate video of this section. It's about an hour, as I recall, to watch this video, and then I'll have some time in class the next day for sort of Q&A, because I want it to be a contact thing as well. So if you have as you're watching that video this weekend, prepare questions that you might want to ask in class. Yes.
So will it be on the exam?
No, it will not be fair game for the exam because it's not going to be done until the weekend, and the cutoff for the exam will be Thursday. That's right. And there was another question. Was that the same question for everybody?
Yes.
Yeah, okay, perfect. Okay, so anyway, we're going to be starting next time with Chapter 3. Okay, see you later.